So far in this unit, we've discussed doing a U-sub for possible methods of integration. We've discussed trig identities, integrating sine and cosine, things of that nature. We've discussed long division, divide and conquer with fractions, and integration by parts. And what we're going to do now is use some integration techniques dealing with trig identities and how to manipulate those trig identities in an integral. Let's take a look at some real common trig identities. The first identity we want to look at is the trig identity for graphing a circle. Sine squared x plus cosine squared x equals 1. And if we wanted to rewrite that, we could rewrite that for cosine squared x by taking the sine squared x to the other side. Or we could write it for sine squared x by taking cosine squared x to the other side. And so with this trig identity, we can replace even powers of cosine or sine of x with the alternate expressions and eliminate then either the cosine of x from an integral or the sine of x from an integral. Likewise, if we look at the trig identity 1 plus tan squared x equals secant squared x, and we can get that by just taking this and dividing it by cosine. Then we can solve this for tan squared x, and we can solve it for secant squared x. So if we wanted to solve this for tan squared x, we take the 1 to the other side. And if we wanted to solve this for, I guess, 1, we could take tan squared x to the other side. And these trig identities that pertain to secant and tangent we'll look at in the next video. The other substitutions then are these two substitutions, and it is to work with dealing with when we just have exactly sine squared or cosine squared x. And so if we would solve these then, and then not really solve them, but express sine squared x as 1/2 minus cosine 2x over 2. Then we can also work with integrating even powers or sine x and cosine x to exactly a power of 2. That's when we have to use this this double angle formula for when we just have sine squared or cosine squared x. So those are the 4 major identities we're going to use. The stuff in blue here we'll save for the second video. When we look at then even powers of cosine or even powers of sine, what we want to do then is we want to try to express our integral as multiple powers of even powers of sine or cosine. So like a sine squared x, sine to the 4th x, sine to the 5th x, or 6th x, etc. So what we're looking to do then is we're looking to reduce expressions when the powers are odd. And so if n is odd here, if sine is raised to an odd power, what we're going to do is we're going to express it as sine of x times some multiple of sine squared x. So that multiple might be like, sine to the 4th, it would be sine squared x squared, or sine to the 6th, it would be sine squared x cubed, something like that. And then what we can do, so this might be, for instance, writing sine to the 6th x, or let's say writing sine to the 7th x as sine x times sine to the 6x, where sine to the 6x can be re-expressed as sine squared to the cubed power. And what that does then is it allows us to kind of save a sine x, and if we save this sine x here, then what we can do is we can convert this expression to a cosine. So if we would kind of save this sine x here, so we're going to save one sine x, then what we can do is we can take this and we convert the rest to a cosine. So this would end up being converted to a cosine. And then we can do a u sub, and we'll have a sine x dx for our u sub for a differential expression. And likewise, the other scenario is when we have an odd power. When we have an odd power for cosine, we do the same thing for the cosine. So here's the odd power for the cosine. So we split it up as cosine times cosine squared x, some multiple of that. So, just envision replacing all of these with cosines instead. Cosine to the 7th x would be cosine x plus times cosine to the 6x, which would be cosine x times cosine squared cubed. And again, the whole idea here is to save that odd power. So we're going to save one cosine here to substitute out any u sub, and then we're going to go ahead and convert the rest to an even power, the rest of the even powered cosines to sine. And then just kind of a note here, kind of what I was speaking to up here, is if no odd powers, then we have to use that double angle formula that I was talking about a moment ago. If we look at this first example here, we see that we have a cosine x to the 5th power. So there's our odd power. And so we're going to rewrite that as cosine x times cosine to the 4th x. And so that is going to be cosine x times cosine squared x squared, and this is what we're going to substitute out. So this integral then becomes sine squared x times cosine x times cosine squared x squared dx. And then what we're going to do is we're going to take this cosine squared x, and we're going to use our trig identity to substitute that out. So our integral now becomes sine squared x times cosine x times 1 minus sine squared x quantity squared dx. And so if you notice, everything is in terms of sine x except for this. And so I'm just going to rearrange this. Sine squared x 1 minus sine squared x quantity squared cosine x dx. And what that allows us to do now is it allows us to do a u sub, where we're going to let u be sine of x. And so if u is sine of x, then the differential du is going to be the derivative of sine x, which is cosine x dx. And so that allows us to get rid of that remaining cosine, that remaining cosine here. And so substituting, doing our u sub here, we end up with u squared 1 minus u squared quantity squared du. And so now it just ends up as a simple polynomial expression. So we're going to have to go ahead and FOIL this. So that's going to be 1 minus 2u squared plus u to the 4th du. I forgot the power of 2 on this right here. And then we're going to have u squared minus 2u to the 4th plus u to the 6th du. And so we can go ahead and integrate that like we would integrate any polynomial expression. So this would be 1/3 u cubed. This would be minus 2u to the 5th over 5, and plus 1/7 u to the 7 plus c, and then substituting back in our value for u, which is sine of x, we have 1/3 sine cubed x minus 2/5 sine to the 5th power x plus 1/7 sine to the 7th power x plus c. If you notice with this problem, there are no odd powers. That being the case, we have to use the double angle formula. So the double angle formula for sine squared x is 1/2 minus cosine of 2x over 2. And so that's for sine of x. We have sine of 2x. So that being the case, we would have sine squared of 2x, which means everywhere we see an x, we have to replace it with a 2x. So we end up with the expression 1/2 minus cosine 4x over 2. So that's what we have to substitute into the integral here. So we have the integral of 1/2 minus cosine of 4x over 2 dx. And the whole idea of substituting this in is to eliminate that power, because as long as the trig function stays in the expression, we can't have the powers in there and still be able to integrate it without doing a u sub. And so when we look at this one, then integrating this with respect to x, we get 1/2 x minus, and I'm just going to leave this in the integral for just a minute here, because what we need to do is we need to do a u sub on the 4x. So if we let u equals 4x, and this is a calc AB skill, right? Then our du equals 4 dx. So we need a 1/4 du out front to substitute out our dx. So this is going to look like 1/4 out front cosine of u over 2 du. And now we can go ahead then and integrate that, and the integral of cosine is sine. So we can go ahead and say this is 1/2 x minus, I'm going to pull out the 2, so it's going to end up being 1/8 sine u, and substituting that back in terms of x, don't forget your constant of integration there, we get 1/2 x minus 1/8 sine 4x, make sure to use your brackets there, plus c. Verify our formula. What we have to do is we have to prove that the left hand and the right hand equal the same value. So in looking at this, what we really need to do is evaluate this expression cosine to the 5th power x dx, and see if in fact it does really equal 8/15. So that is the big question, is whether or not those two are equal. So what we have to do is we end up having to integrate this side here. And so if we look at this expression here of pi over 0 to pi over 2, we need to substitute out this these even numbers of, or even powers of pi. So we're going to split this up as cosine of x times cosine to the 4th x dx, and that way we have our odd power of cosine to substitute out. So this is cosine of x times cosine squared of x squared. And so this ends up being cosine of x 1 minus sine squared of x squared. And so now we have a cosine x dx to substitute out. So we're going to do a u sub here. And our u sub is going to be u equals sine of x. And then our derivative then is du equals cosine x dx. We have a cosine x dx to substitute out. So taking a look at that expression, it now looks like 1 minus u squared du. And I'm going to leave the limits of integration off for a while because 0 to pi over 2 refer to variable x, not the variable u. So I'm going to go ahead and FOIL this. So we got 1 minus 2u squared plus u to the 4th du, and then I'm going to go ahead and integrate this. And then we'll worry about the limits of integration in just a minute. So this would be 1/3 u cubed. This would be 1u, or just u. This would be 1/5 u to the 5th. So we end up with u minus 2/3 u cubed plus 1/5 u to the 5th. And when we substitute sine of x back in, we have sine of x minus 2/3 sine cubed of x plus 1/5 sine to the 5th of x. And now we have to evaluate that from 0 to pi over 2. And it looks kind of like a complicated expression, but really when we're talking about sine of x, we know that the sine of 0 is 0, and the sine of pi over 2 is 1. So we can just look at substituting in those values. So at pi over 2, we have we've got the sine of pi over 2. And then we've got minus 2/3 sine cubed of pi over 2. And then plus 1/5 sine to the 5th of pi over 2. And then we have to subtract the value when we plug in 0. And we know that sine of 0 is 0, we know that sine cubed is 0, we know that sine to the 5th is 0, so I'm just going to plug in a 0 to represent that entire expression with 0 substituted in. So when we look at evaluating this here, sine of pi over 2 is 1, sine of pi over 2 is 1, 1 cubed is still 1, so we got 1 minus 2/3. Sine of pi over 2 is 1, to the 5th is still 1, so plus 1/5. So if we look at that, common denominator is 15, so we've got 15 over 15 minus 10 over 15 plus 3 over 15. We end up having 8 over 15, which confirms Wallace's formula back up at the top of the page of 8 over 15. In this example, we're using the trig identities dealing with sines and cosine products with different angles. So if we look at this example here, we have the sine of minus 4x and the cosine of 3x. So that falls into this category here, where we have the product of a sine and a cosine. And we're missing any powers, so we can't use the traditional identities that we think of when we think of trig functions. And so in this case, we have an m equal to a negative 4 and an n equal to a positive 3. And so we can rewrite that as as this product here. So, and that what that allows us to do is I said that wrong. We can write it as a sum here. It allows us to take a product of two functions and write it as a sum of two functions. So sine of minus 4x times the cosine of 3x ends up being 1/2 sine of m minus n, so that's going to be minus 4 minus 3x plus 1/2 sine m plus n, so minus 4 plus 3x. So that ends up being 1/2 sine minus 7x plus 1/2 sine minus 1x. And so it takes what was a product and makes it a sum. And how that helps us is that there is no u sub that will allow me to solve for this product. But if it's a sum and each one only has one trig function, then it turns into a real simple integration. So to integrate that, I'm going to pull the half out front, and all I have to do now is integrate sine of minus 7x dx. And then add to it the integral, pulling out the half again, the integral of sine of minus 1x dx. There we go. And so as we integrate that, and we could do a quick u sub here. We could say u is equal to minus 7x here. So du is minus 7 dx. So this ends up being 1/2 times 1/7 sine u du. And this ends up being 1/2 times, and we could do a u sub here too with the -1. So the du is a minus 1 dx. And all that does is pull out a minus 1. And then we have sine of u du. And then we can go ahead and integrate this. So we get 1/14, and the integral of sine is then opposite cosine. And then we have a minus 1/2 here, opposite cosine. And just be careful about the u's here. I probably should have used a different variable. But just to make sure you get the right substitute back in, this ends up being cosine minus 7x. And this ends up being a minus and negative, it ends up being a plus. So we're back to a positive 1/2 here. Cosine of minus x. And then plus our constant of integration. So just to sum up the techniques that we know so far, for this chapter we've gone through U subs, we've gone through trig identities, we've gone through long division and divide and conquer, integration by parts, and now we can add to it these trigonometric integrals that we're solving in this section.